Hello and welcome everyone to Calculus Notes 1.3. This is evaluating limits analytically. So we used our first two methods of graphically and numerically last time, looking at the graph and then plotting a table of values. And this time we're going to see how we can use the equations themselves to find specific limits. So we're going to be doing this using direct substitution today. Okay, so when f of x, our function, is continuous at point C, you can simply substitute C in for x to find the limit. Okay, so then the limit of our function f of x as x approaches C is f of C, meaning you just take this C right here, you plug it in for x in the function, and whatever answer you get out is the limit. Now, this idea of continuous, we're going to talk about a little bit later on in the chapter, and we'll briefly touch on that now. So if we just have some sort of curve here, okay, it can be anything, and this is our function f of x. Now what it's saying is if we choose a C, we'll just choose C to be right here, and this function is continuous at this point, so we can kind of see here this function continues along, we get to the point and then it continues on. So if that's the case, if it's continuous right there, then the limit is actually going to be this y value, or f of c. Okay, so that's kind of what we're looking at. So direct substitution is going to work for all polynomial functions. Woohoo! It works for all rational functions as long as C is in its domain. So it's a good thing we talked about finding x values in a specific domain. It also works for functions that involve radicals as long as C is in its domain, and for trigonometric functions with C in its domain. So some things we've got to watch out for in rational functions is the dreaded divided by 0. Okay, that is the only time if C gives us this that it's not going to work. Functions involving radicals, okay, some things to watch out for is if you have an even index right here, you cannot have a negative. Okay, so we can't take the square root of a negative number. So that is also something to watch out for. For trigonometric functions, we just have to watch out for things like the tangent function, because there are places where the function is not defined. Okay, so we got to watch out for those. So let's take a look at a couple of these. So here are some very basic limits, and these are actually all polynomial functions here. So we know it's going to work for all of them, but they might just throw some tricky things here. So this is the limit of b, and b is just a positive integer. As x approaches c, well, b still equals b. For number 2, here we just have a straight line, or it's just x, so the limit of x as x approaches c is going to just be c. And here we have some exponent, and notice that n has to be positive. Okay, so here we would just plug c in for n. Here we would plug c in for x and get c to the nth power, and that would be our limit. Now notice, if we had this, if we had x to the negative n, we know that our laws of exponents would flip this over, and all of a sudden this would become a rational function, and then we'd have a whole different story. All right, so let's take a look at some other properties. Now, for the functions f and g, so now we have two functions happening at the same time. If the limit of f of x as x approaches c and the limit of g of x as x approaches c both exist, then all of this stuff is going to be true. And it's basically saying that if we multiply, okay, we just take a number and multiply it by our function, the limit is just going to be the same. So it behaves very much as we would expect. If we add or subtract our two functions, okay, the limit would be as if we took the limit of each and then added them together. Same thing with product. If we multiply our two functions and take the limit, it would be the same as taking the limit of each one and multiplying them together. The quotient, if we take the limit of our two functions divided by each other, it's going to be the same as taking the limit of each of them and dividing them. One special note here is that the limit of g of x as x approaches c couldn't equal 0. Okay, so that would have to be non-zero for that to work. For the power, if we raise a function to a power and then find its limit, it's the same as finding the limit first and raising it to the power second. For composite functions, so we're finding the limit of f of g of x, that would be like finding the limit of g of x first and then plugging that into function f. So all of this stuff just behaves very much the way you think it should. So let's try some examples here. The limit of 3 as x approaches 2. Well, this is just a constant, so it's just going to be 3. That's one of our basic limits. Here, the limit of x as x approaches negative 4 is just going to be negative 4. Again, one of our basic limits. Here we have a simple exponent, so the limit of x squared as x approaches 2. We can use direct substitution here, and we get 4. Moving on, letter D, this is a polynomial function, so we know direct substitution is going to work no matter what. So we're going to go ahead and plug in 2 here for x and evaluate. Okay, so we know the limit of 4x squared plus 3 as x approaches 2 is going to be 19. For letter E, this one here is a rational function. So you can see that it's a polynomial divided by another polynomial. Now, direct substitution is going to work as long as this value c equals 1 is in the domain of this function. Okay? So really what we're doing here is we're looking at the denominator here. And if we plugged 1 in for the denominator, we get the value of 2. So therefore c is going to be in the domain, meaning direct substitution is going to work. So we're going to plug 1 in for all of our x's, and then go ahead and solve. So this is 1 plus 1 plus 2, which is 4. 1 plus 1 is 2. 4 over 2 is 2. Okay, so with a rational function, just check and make sure that c is in the domain of the function. Letter F, here we have a radical. Okay, so we again have to check and make sure that 0 is going to be in the domain of this function. So the only thing that matters here is 0 going to make the inside negative? Well, 0 squared is 0, plus 4, that's positive. So 0 is in our domain again. So we can use direct substitution. So this is just going to equal 0 squared plus 4, which is the square root of 4, which is 2. All right, moving on. Letter G. Now we have a trig function. And again, if that 0 is in the domain of the tangent of x, then we can use direct substitution. Okay, so 0 is in the domain because the tangent of 0 equals 0. So therefore the limit of tangent x as x goes to 0 is just 0. Now looking at our next one, here we have x times cosine x. So this is going to be the property where it's multiplied, so we could find the limit of x as x goes to pi, and then the limit of cosine x as x goes to pi, and multiply those together. Now it turns out that pi is in the domain of the cosine, so we can just use direct substitution. And we get pi times cosine pi. Okay, cosine of pi is -1. So our limit is -pi. Moving on, here we have the limit of sine squared x as x goes to 0. Now, anytime you see this sine squared, you're going to want to think about it like this. I'm going to rewrite our limit. So sine squared x really just means the sine of x squared. So this is just a shorthand way of writing it, but this is really what we're looking at here. So we just want to think, this becomes a polynomial function here. So all we have to do is check, make sure 0 is in the domain, and it's going to work. So we're just going to use direct substitution here. We're going to take the sine of 0, and then we're going to square it. So the sine of 0 is 0. 0 squared is also 0. So our limit is 0. All right, I want you to go ahead and give A through E a try on your own under the Try It section. And then you can pause the video, come back, and check your answers. Welcome back. Here are your answers. So you can pause the video again and you can check your work and just see how you got. Remember to jot down any questions you might have, and we can get those answered in class. All right, moving on. Now we're going to talk about rational functions and functions with radicals without c in the domain. So if c is not in the domain, direct substitution into our function is not going to work. But what we're talking about here are functions that agree at all but a single point. So it says let c be a real number and let f of x equal g of x for all x that are not equal to c in an open interval containing c. So let's see what that means. If we're looking at a function, let's just say there's a hole in the function right here at c. We'll call this f of x. Now what this is saying is if there is another function, a g of x function, that's exactly the same as this function at every point except this one, then we can go ahead and just plug c into that nearly exact function to find our limit. Okay, so again, graphically we can see that it's going to this point right where the hole is. And numerically we could find that. But if we can find another function that's here in blue that is exactly the same on all points, but actually contains this point where that hole is, then we can use direct substitution in that g function. So here's the process kind of outlined for you. So we can't determine direct substitution, so we try to find a function g that agrees with everything except x equals c. So what we have to do when we're finding this can be accomplished sometimes by factoring or rationalizing the numerator and then simplifying. So what we're talking about here is we're going to be getting rational functions where we would get 0 in the denominator. So if we can somehow alter this equation to where we wouldn't get the 0 down here, then we can try direct substitution in this new function, g of x. All right, let's try some examples. This will become a lot more clear. So we want to find the limit here of x cubed minus 1 over x minus 1. So this is our rational function. And you'll notice if we plug 1 in for x, we get 1 minus 1 in the numerator, and so direct substitution fails. So I'm just going to write ds fail here, just to remind us we can't plug in 1. So what we want to do here is factor the numerator. Okay, so x cubed minus 1, you're going to have to recall a difference of cubes, how to factor that. And we remember the acronym SOAP, for same, opposite, always positive. Okay, so we're going to rewrite this. The limit as x goes to 1, and we get x minus 1 times x squared plus, here's the opposite sign, and this is 1 times x, and plus 1. And this is all over x minus 1. Now you'll see what we've done here is by factoring we can now simplify this by canceling out the x minus 1's. And so now we're just left with the limit as x goes to 1 of x squared plus x plus 1. And this is that g of x function we were talking about earlier. Because it's just a polynomial, we can use direct substitution here, and we find that the limit is 3. All right, let's try another one. So we have a rational function. We try to plug 1 in. We get 1 squared, which is 1 minus 1 is 0. So we get a ds fail. So what we're going to do here is actually factor both the top and the bottom. So we get the limit as x goes to 1, and yes, you do want to rewrite this every time because that's what we're trying to solve. We'll factor the numerator, and then we're going to factor the denominator. And then we're going to simplify, and so you can see our x minus 1's are going to cancel out. And so we're left with the limit as x approaches 1 of x plus 2 over x plus 1. If you notice now, if we plug 1 in to that denominator, we get 2. And so x, or c, is now in the domain, and so we can use direct substitution on this rational equation. And so we're going to plug 1 in here, and we're going to get 3 over 2 as our limit. So let's look at example C. Here we have a rational function with a radical in it. And so if we try direct substitution here, let's just put that up here and see what we'd get. We'd have 0 plus 1 minus 1 over 0, which turns out to be 0 over 0. Now you might think, well, 0 divided by anything is 0, okay, but it doesn't quite work that way when 0 is in the denominator. And we call this an indeterminate form. So this is not a solution in this form, it's indeterminate. And one of the last things, the last thing we're going to do in calculus this year is something called L'Hopital's rule, and it's going to help us how to find this limit of an indeterminate form. But for now, we're going to stick with our approach of factoring or rationalizing the numerator. So looking at this, you've seen square roots before and we've had to rationalize, so that's what we're going to do here. So we want to get rid of that square root symbol. And it's the same process that you did before, where all you have to do is multiply by the change of sign right here. So it's going to be the square root of x plus 1 plus 1 instead of minus 1 here. And then to make sure we're not actually changing the values, we're going to multiply by 1, meaning the numerator and the denominator have to be the same here. Okay. Now, just for recall, if you have this situation where you have a plus b times a minus b, you'll notice that's the difference of squares. So you're going to get a squared minus b squared here. So that's going to help us to perform this operation. So let's rewrite the limit as x goes to 0. And here's a and here's b, and it's going to be a squared minus b squared. So we have the square root of x plus 1 squared minus b squared. And that's going to become our numerator. The denominator, we're actually going to leave this factored. So we don't want to multiply that together. It might just confuse the issue. So we're going to leave it just like this for now. Let's go ahead and simplify this a little bit. Don't forget to write the limit as x approaches 0. Okay, square of square root, and we've got x plus 1. And this is going to be minus 1. Notice the negative on the outside here is going to change the sign after you square it. And we're going to leave our denominator the same for now. Okay, and you can see here plus 1 minus 1, so that's going to be gone. I know it's a hassle, but we're going to write the limit as x approaches 0. And so our numerator, we're left with x. And hopefully you can see here that we can cancel out our x's. So the limit as x approaches 0 is now equal to 1 over the square root of x plus 1 plus 1. Now, we still have a rational function and it still has a radical in it, but is 0 in the domain? Well, we plug 0 in here. 0 plus 1 is 1. The square root of 1, that's fine. That's 1. 1 plus 1 is 2. And so we can see we can use direct substitution now to solve this out. So we're going to plug 0 in for x. And we get our limit of 1/2. So it requires a little bit more work, but this is how to rationalize the numerator so that we can simplify and come up with our limit. All right, I want you to try A, B, and C on your own. You can pause the video and come back and check your work when you're finished. All right, welcome back. Here is the worked out solutions for A, B, and C. So take a look over your work and remember to jot down any questions you have, and we can go over these in class. Moving on to our final topic for this section is special trigonometric functions. So these are just going to be defined for you here to use in finding other limits. So the limit of sine x over x as x approaches 0 equals 1. We also have the limit of 1 minus cosine x over x as x approaches 0 is equal to 0. So these are just some that are defined for you, and I'm going to show you how we can use these to find other limits in our next example. So it's the limit of tangent x over x as x approaches 0. You can see if we try to plug in 0, we get a, ds, fail. Okay, so we get 0 over 0 indeterminate form. Now for this example, we see a tan here, but the limits I gave you have sine and cosine in them. So we're going to try to change our tangent into sines and cosines. So recall that the tangent of x is the same thing as sine of x over cosine of x. And we could actually rewrite this like this: sine of x times 1 over cosine x. And that's the same thing as tangent x. So we're going to rewrite this now using sines and cosines. So we have the limit as x approaches 0, and tangent x we're going to rewrite as sine x times 1 over cosine x, and then we're going to leave the divided by x right here. So hopefully you can see that we didn't change this equation. We just rewrote it using this equality right here. Now, this is two different functions that are being multiplied together. So we can actually split this apart and find the limit as x approaches 0 of sine x over x, and we can multiply that by the limit as x approaches 0 of 1 over cosine x. Okay, so if you need to review those properties, they're way back on the first page. So looking at this, what's the limit of as x approaches 0 of sine x over x? Well, it's right up here. It equals 1. So we know this whole thing equals 1. Now in this case, we'll use direct substitution. 1 over cosine 0. And cosine 0 equals 1. So we have 1 times 1 over 1, which is just 1. So it's kind of an interesting way where we transform our function so that we can use these special trigonometric limits. Now looking at example B, we can see the direct substitution fail when we plug in the 0. Now, for this to work, all that has to be true here is that this number is the same as this number. And right now it's set up so that this number is 4 times the amount of this number. So we need to get this number and this number to be the same. Then we could say that it equaled 1. So in just thinking about this, really what we have here is 1 over x. We need to get this to be a 4 down here. Okay, so to do that, what we're going to do is actually multiply by 1/4, and then we're also going to multiply by 4 over 1. Okay. Did we change 1 over x? Well, 1/4 times 4 over 1 is 1, so we haven't changed anything. But now we can rewrite this as 4 times 1 over 4x. This is going to be a method we use quite often in calculus, especially when we get to integration in second semester. So if we need to have that 4 in the bottom, okay, we can put it in the denominator as long as we multiply by 4 on the outside. Okay, so it's a little trick that we're going to pick up early here. So let's go ahead and do this right here. We have the limit as x approaches 0. We're going to go ahead and multiply by 4. We still have the sine of 4x. And then on the bottom, the denominator, we're going to multiply by 4. And you can see if we multiplied this out, we would be left with our original equation. Using another property from that first page, we can take that 4 to the outside. So that scalar multiple doesn't necessarily change how we find the limit, but it does just multiply at the end. So now we have sine of 4x over 4x. So here's where you really have to understand when you're dealing with variables in equations that they're just numbers. So if you have x over x, x is just a number and it's the same thing. So looking at this, 4x is just a number like x was, and 4x down here is the same number. And so this is the same thing as this. And so we really have 4 times 1, and our limit then is 4. All right, I want you to try A and B down below on your own. When you're finished, come back, unpause the video, and check your work. All right, welcome back. Go ahead and check your work here. You can pause your video and see what you're doing. Again, jot down any questions you might have, anything you're unclear on, and we'll go over it in class. One note at the bottom, remember, you can always use a graph or a table of values to confirm the limits that you find. So if you worked all the way through this and you got 0 and you wanted to make sure that that was true, go ahead and just type this into your graphing calculator and verify that as it approaches 0 from the left and the right, you actually get 0, and that will always work. Again, you can also use a table of values, start picking numbers closer and closer to 0, and see if it indeed is heading towards 0. All right, that's been finding limits analytically. Thanks for watching, and we'll see you in class.